Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and today I'm going to cover lines and planes in 3 space. So a line in 3 space with initial vector r0 and in the direction of v0, having parameter t is given in vector form by, so this is a vector form equation. It's r of t, which t is going to be that parameter, is equal to that initial vector plus, we'll say the direction vector, but really parallel to that direction. Because a lot of times in Calc 3 we say direction, we mean unit vector, but it doesn't have to be unit vector. So this is going to be the initial vector plus its direction vector times t. Now this is its vector form. We can also expand this into its component form. So r0, we'll say this is equal to x0, comma y0, comma z0. And then this will be plus our directional vector, which is going to be, say, v1, comma v2, comma v3. And this is all going to be, well, this vector is going to be multiplied by t. So I'm going to give it to you graphically so you can have an idea what this means, and then we'll write this in another way as well. So what we have is we have in 3 space your x, y, z axes. And if you remember back in like algebra, we'd ask, what things are needed for the equation of a line. Well, what's needed for the equation of a line is going to be, a point and a slope. And that's all fine and good when you're working with just 2D space, because if I have an initial point and then if I have a slope, which is going to be your rise over run, really that slope kind of gives you your direction. So I'm going to start here, and then my next point, I'm going to have to go, up something, then over something to be able to find the next point. So very similar for a line in 3 space. What you need is an initial point to start at, and then you need to know what direction you go. But since we have, 3 open directions here, we're going to have to do a direction as being a direction that's going to be parallel to what way we want to go. So our initial vector is going to be this x0, comma y0, comma z0, and it's going to look like this. I'm just going to take this out into the space, and this is going to be that initial r0 vector. And then I'm going to have to go in the direction of this v0. So what that means is, say this is v0, this would just be, say, one of those v0s. And then I'm going to multiply this thing by t. So that means it's not just one of it. It could be, it could be 2 of it. Or it could be 3 of it. Or it could be -1 of it. Or -2 of it. So what we can see is from this initial, we'll say point, but it's kind of drawn by the vector. We can see that we can get a whole bunch of points here. So, the initial one, and then the initial plus the, 1 times this, the initial plus 2 times this, the initial plus 3 times this. And you can see that we're really doing a bunch of collinear points. So our line is going to be, this particular line. I tell my students, if you kind of remember playing with sparklers as a kid, so you're lighting the end of that sparkler, you're kind of waving it around, and you can kind of think of that sparkler starting at the origin, and when you move this thing around, the smoke that comes off of it is what's going to draw your picture. Well, that's kind of what's going on here, that, the sum of these 2 vectors, this is going to be the tip of that vector after you do this, these 2 operations. So really, you kind of think of like the, your smoke pattern. So that's why, you do your initial plus t times any one of these. Okay, so I can write this in a couple different ways as well. So since these are 2 vectors, and I know that t is really just a scalar, I can send t through this v vector. So this is now going to be equal to x0, comma y0, comma z0, and then plus our v1 times t, v2 times t, and v3 times t. And now, since we're summing these 2 vectors now, this vector plus this vector, I can just add the components together. So what I'll get is x0 plus v1t. The middle component, or the y, is going to be equal to y naught plus v2t. And then finally your z naught plus v3t. Which allows us to write this in a parametric form just by isolating its component. Like the first component, your x component, is going to be equal to x naught plus v1t. Your y component is your y naught plus v2t. And then finally, your z component is going to be equal to z naught plus v3t. Okay, so let's get a little practice. It looks nice when we have this expanded out, but really kind of the goal is, if I give you a couple points, can you give me an equation of a line in 3 space? So let's do that. So here's our example. I want to determine a line in 3 space that passes through these 2 points, so the point A and the point B. So in order to find an equation of a line, let's write it up. R of t is going to be equal to, this is going to be R naught plus, to make sure that doesn't look like a B, so R naught plus V naught times T. So what I'm going to need, again, and I ask students all the time, like, what 2 things do you need for a line now? Well, we're going to need an initial point, and we're also going to need a direction. So our initial point can be any one of these 2. You can use this point, or you can use this point. So in general, we usually pick the easiest of the 2 points, or sometimes we just say, always just use point A and just stay consistent. So now this is the point A. What I need is the initial vector that starts at the origin and maps to A. So it's the same exact coordinates. So our R naught is going to be equal to -1, 0, and 4. So this will be our initial vector that maps to that point right there. Now plus, in order to find V naught, what I'm going to need is I'm going to need to know the direction from A to B. So what I'm going to have is, I have 2 points. I have the point, -1, 0, 4. And then let's say, just for 2D sake, we'll say this is 3 minus 2, 5. I'll draw the scale, vector orientation. So what I already know is my first vector, goes from the origin to this point. So that's this piece right here. Now the next one I'm going to need is my direction vector. So I'm going to have to go from here to here. I need that direction vector. So this being R naught, and this being R V naught. Okay, so in order to find V naught, we have to do final minus initial. So I'm going to have to subtract our corresponding coordinates. So in order to find this is going to be equal to 3 minus a -1, comma, now I have -2 minus 0, and then finally 5 minus 4. Now remember, this all still has to be multiplied by t, because I don't really just want to stop here. What I need to do is I need to, if I plug in t equals 0, it'll be this point. If I plug in t equals 1, it'll be this point. When I plug in t equals 2, it's going to be this point. T equals -1, it's going to be this point. So what I'm really looking for is I'm looking for this full line, which is going to be, this R of t. And then I'll kind of prove it. I'll plug a couple values in, and you can see that this actually is going to work itself out. Okay, so simplifying this, we know that I can subtract these coordinates in our direction vector. So this is going to be equal to -1, 0, and 4. And then plus, 3 minus -1 is going to be a 4. This will be -2, and this will be equal to 1 times t. And that's fine. There's nothing wrong with that vector if we want to write it this way, in this vector valued form for our line. Now we can also parameterize the line. So I can also say, or writing this in parameter form, what would the x coordinate be? Well, it would be the sum of the the first coordinate. So -1 plus 4 times t. The y coordinate is going to be the sum of the middle one. So 0 minus 2 times t, or we could just say -2t. And then finally, our z is going to be equal to 4 plus 1t, or just 4 plus t. Now again, what I want to do is I want to really check that it does go through all these points here, and I don't need to show them all. Let's just show a couple. Let's say clearly when I plug in 0, let's just see this. Let's make sure it goes through that point right here. Well, when you plug in 0 for t, because t is your parameter, it's what your inputs essentially, is when you plug in t equals 0, this vector is going to be gone here. So I'm just going to get this initial vector, so it's going to stop at this -1, 0, 4. You can check that here. If I plug in t is equal to 0, looking at the same thing. So minus 2t, and then this was 4 plus t. So we can check it. When I plug in t equals 0, this will be gone, so it'll be negative 1. T equals 0, this whole thing will be 0. And then t equals 0, this will be 4, which is what we get here. Our coordinates, negative 1, 0, 4. Now, let's try t equals 1. I'd better get, that second point. So when I plug in t equals 1, we'll just do it here. So when t is equal to 1, this is going to be negative 1 plus 4, which is going to be 3. And then when t equals 1, this is going to be negative 2 times t, which is going to be just negative 2. And when t equals 1, this is going to be 4 plus 1, which is 5. And of course, we can show this for negative 1, we'll get this point. But I really just kind of verifying it's going through these points. So that's the equation of our line, either in vector form or in parameter form. Now, the next thing I want to do is find the equation of a plane. So the equation of a plane through this point x naught, comma y naught, comma z naught with normal vector n, which will be a comma b comma c, is given in vector form by n dotted with the general vector or an arbitrary vector p minus p naught. And we're sorting this dot product equal to 0 because when dot products are 0, we get we force these two things to be perpendicular to each other. So what I want to do is kind of explain where this vector value, this vector equation comes from. So what I have is a point which is going to be x naught, comma y naught, comma z naught, and it doesn't really matter where it is. So this is x naught, comma y naught, comma z naught. And I'm going to just put that normal vector, since I can move it anywhere. I'm just going to put the normal vector right on that dot. So right here. So this is going to be the normal vector. Now, what a normal vector is it's going to be perpendicular to this plane. So that's what we mean to be normal to the plane. Now, what I have is some arbitrary vectors in here. Really means, let's say if I have just some general point that's going to be x, comma, y, comma, z. And this point right here can slide anywhere because I'm not forcing it to be valued, particular values. I really need them to be arbitrary. And what I can say is if I put that point there, or say if I put this point here, it doesn't really matter. What I can tell you is that the vector p minus p naught, which is going to be, I guess, this one right here, final minus initial here, that these vectors will guarantee to be perpendicular because their dot product is equal to 0. So remember, that's going to work for all vectors. So if I have another x over here, it's going to have another perpendicular, or say another x over here, they're going to be, perpendicular, that, this x, comma, y, comma, z can slide around. So I'm really looking at all vectors on that plane because it's got to go through x naught, comma, y naught, comma, z naught. So they're going to be on that plane, but they're always going to be perpendicular to n. So that's what that does for us. Now, eventually what I want to do is write this in equation form. So what we know is that our normal vector is this component form a comma b comma c, and then we're going to dot this with the component form of p minus p naught. So we know this is going to be a final minus initial. So actually I have these drawn in the wrong direction. Let's do this. So we'll get there. So the final minus initial is going to be x minus x naught, comma a y minus y naught, and then comma z minus z naught. Make sure I actually have those drawn in the right direction. Yeah, we're good. So, okay. Now, this is going to be equal to 0. So now when I do this operation, what we're going to have is the dot product says multiply the corresponding components, and then we're going to add those things together. So this is going to be a times x minus x naught. And then we're going to have plus b. So I'm going to get this. It'll be helpful later. Times y minus y naught. And then finally plus c. Times z minus c. Now the only ones I technically want to color is I really only want to color the z naughts, because those are kind of your given points. So we'll say the z minus z naught this way, so z minus z naught. Similarly for the y and also the x's. So x minus and then y minus. Okay, so what I want to do is I want to use this equation and put this into practice. So like a really quick example would be, determine the plane through, let's say, 5 minus 4, 1, with normal. And we'll write this in IJK form because I haven't done them yet. So let's just say this is n is equal to 3I minus 2j plus 7k. All right, so what we know for our plane is we're going to need an initial point, which is right here in orange. And we're also going to need a normal vector, which is going to be in our pink. And really, we're just putting these things into this equation. So this is just kind of explain, why this is a plane. And then this is what we use to compute it. All right, so what I know is A, B, and C are, just these component forms of, 3 minus 2, 7. So if I want to write that in component form. So this is now going to be equal to 3 times x minus, and then we're going to have plus, minus 2 times x minus, y minus, and then finally plus 7 times z minus, and this is going to be equal to 0. Now, remember that our solution point to that plane is going to have to now go in these missing locations because that's your x naught, y naught, and your z naught, which is given by this 5, negative 4, 1. So this is going to be a minus 5, and this is going to be minus a minus 4, so plus 4, and then finally minus 1. What's nice is you can guarantee that it definitely goes through 5, negative 4, 1, because if I plug in 5 here, this term will be equal to 0. Negative 4 here, this term will be equal to 0. Then 1, this term will be equal to 0. So then you'll get 0 equals 0, guarantee that's a solution. And also remember, this is the dot product between this normal vector and then any of these general vectors on that plane. So we guarantee that, that they're all normal to this. So the last example I'm going to do is I want to give you 3 points, and then from those 3 points, I want to be able to find the equation of a plane. So it's a really classic equation. You can almost guarantee that you'll see that in a Calc 3 class when you're learning your three-dimensional geometry or algebra. Right, so here's our example. Determine the equation of a plane through the points A, B, and C. So A given by this, B and this, and C this. So what we have to do is in order to find the equation of a plane, we already know that our plane is going to be, A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to 0. So just like when I'm asking about a line, like what 2 things do you need a line to find the equation of a line? Well, I need a point and a direction. Now it's a little bit different for a plane. What 2 things do you need to find the equation of a plane? Well, I need a solution point and then a normal. So we have a solution point. Heck, we got 3 of them. So choose your favorite. Maybe choose B because it has a 0 in it. But it doesn't matter. You can use this one, or this one. Let's just kind of go with A again, just because we tend to do that usually. But I would recommend using B because it has a 0 in it. It will make this term disappear. And, well, it'll make this y not disappear. So the algebra will be slightly easier. Okay, now there's our point. We're going to use A. And I need a normal. So in order to find a normal, we have to compute something that is going to be perpendicular to this. So let me just kind of draw these 3 points. So the reason why a plane is determined by 3 points and a line is only determined by 2 is if I have 2 points, I can guarantee that a line is going to go through there. Now, if I have a plane, that plane could now, pivot on this line. So I needed to stop it at a particular spot. So if I have 2 points, that's not going to determine a unique plane, but a third one will. So that's what we have here. I have an A, B, and a C. Now, what I'm going to do is I'm going to create a normal to this. So in order to do that, we're going to create a couple vectors. So I need this vector right here. And I'm also going to need this vector right here. Let's call this one AB, because this will be the point A. That's fine. This will be the A. This will be B. And then this is going to be A, so therefore this will be C. So this will be the vector AC. And I'm just starting at a common point. So I'm going to say I'll start at A. So I'll do AB, and then I'll also do AC. But again, it doesn't matter. You can do BC, as long as you start at B both times. So in order to find these things, I know that AB is just going to be, final minus initial. So minus 7 minus 2. So minus 7 minus 2. And then I have, oops, sorry, I did AB. That's wrong. That was AC. We'll find that in a minute. So 3 minus 2. And then our second component is going to be 0 minus 1. So 0 minus a negative 1. So it's going to be 1. And then finally, our third component is going to be negative 5 minus 4. So then we're going to have the vector 1, 1, and then minus 9. Now, AC will just do a little more shortcut. So minus 7 minus 2 is going to be negative 9. And then I have 2 minus a minus 1, which would be 3. And then 1 minus 4 is going to be negative 3. Okay, I have two vectors, and we know we can compute something perpendicular to them, say this vector right here, by taking their cross product. So cross products will give you a vector perpendicular to the two vectors you're crossing it with. And using the right-hand rule, if I'm going to go from AB to AC, I can see that this thing is going to point up. If you go the other way, it'll just point down, but it's still a normal vector. So again, you have options. All right, so let's find that normal vector. So this normal vector is going to be computed by doing the determinant of this 3 by 3 matrix, and I showed you how to do this in a very recent video. So our first vector that's going to go in here is going to be 1, 1, negative 9. The next vector is going to be minus 9, 3, negative 3. And then when we compute this is going to be equal to I times I. Now covering up this, it's going to be, let's just do the vectors. I should say the matrix. So I have 1 minus 9, 3, negative 3. Minus j, covering out the middle column, it's going to be 1 minus 9, minus 3. And then plus k times 1, 1, minus 9, 3. So this is going to be equal to I times, now we're going to multiply the main diagonal and subtract it by the multiplication of the other diagonal. So this is going to be minus 3 this way, and then it's going to be minus a minus 27, so plus 27. Minus j, similarly, this is going to give us negative 3. Is that right? Yeah, because I got two ones. And then I have minus a positive 81, so it's minus 81. These are big, whatever, doesn't matter. So plus k times, this will be 3 minus a negative 9. So what we're going to get here is 27 minus 3 is going to be 24i. Minus, this is going to be negative 84 multiplied by a negative, so this would be plus 84i. Sorry, j. And then finally, plus 12k. Now remember, this is our normal vector, so I'll just put it in pink. These are going to be our coefficients. So 24, 84, and your 12. So finally, our plane is going to be written as, I'll write the equation up here. This is going to be A, B, C, and then we have x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. So I know my A, B, and C. 24, 84, 12. 24, 84, and 12. And then we're going to do x minus x naught. So x minus plus 84, y minus plus 12, and z minus is equal to 0. So now we have to put our initial point in here, and let's go ahead and choose this point right here. So this is going to be 2, negative 1, and then finally 4. And again, I could have chose this one, or this one. When you simplify these things, which I mean expand it and get rid of these parentheses, it won't matter which one of the 3 points you got. It'll simplify to the same thing, and I recommend you test it for yourself. So this is, simplifying. This is 24x minus 48 plus 84y plus 84. And this is going to be plus 12z minus 48 is equal to 0. So what that allows us to do is we can just keep our terms with our variables on one side, and then everything else to the other side. So what's that on? Negative 96. So this would be a negative 12 when I send it to the other side would be equal to 12. It actually looks like everything is divisible by, let's make sure, minus 48 plus 84. Good. And then 84 divided by 12. Sure is. So everything's divisible by 12. So this will be, am I going to be able to fit it? Try 2x. 84 divided by 12 is plus 7y. 12 divided by 12 is just going to be z is equal to 1. Hopefully we fit that in there. So just in case they didn't reach it, so 2x plus 7y plus z is equal to 1 was the solution of that particular plane. So if you like the content, please consider liking, subscribing, and sharing. Thank you.